Okay, so part 2 of the general properties of waves section covers refraction and diffraction. And before that, we're going to talk in general about what all waves can do. You're very often asked for examples of similarities between waves, so this is a useful list for that. All waves transfer energy from one place to another. We mentioned this in the first video. And there's no transport of stuff, so no material is moved when this happens, just the energy. All waves can reflect, so bounce off certain types of surface. All of them can refract, and that is change direction and speed when moving from one material, which is called a medium, to another. So, for example, from light moving from air into glass or glass into air would exhibit refraction. Water waves moving from deep water to shallow water would also see refraction, because changing from deep to shallow counts as a change of medium, even though it's the same material really. And finally, all waves will diffract, so they will spread out when travelling through a gap or round an edge. We're going to concentrate on talking about what happens when they go through a gap in this video, and then when we come on to look at uses of different parts of the spectrum, we'll cover an example with diffraction round an edge. Okay, so refraction first of all. So we said that this was the change of direction from air into glass. Or glass into air when you change medium. Okay, so we're going to use the example of light. You may have done this practical with a glass or a perspex block. We draw the incoming ray, that's called the incident ray, and then whenever you're doing a ray diagram, whenever the ray meets a surface, you draw something called a normal, which is a line at 90 degrees to the surface. So that red line is a normal. And then, because the wave goes slower in the glass block, it will also bend towards the normal, so there it is going more slowly through the glass block. All angles in refraction are measured relative to the normal, and that's the same for all ray diagrams in reflection as well. So that angle I is the angle of incidence, and that angle R is the angle of refraction. Okay, and obviously as well, you can see that the angle R is smaller than the angle I. So what we say is the law of refraction: the wave slows down and bends towards the normal, meaning that R is smaller than I, going into a denser medium. So glass is denser than the air, and so the wave slows down, and it will speed up again, going from the denser medium back into the less dense medium. So if we see what happens to this ray as it leaves the glass block and goes back into the air, we draw our normal again, just like before, and this time it bends back the other way. And hopefully you can see that the first ray and the third one, the ones that are both outside the glass block, are parallel to each other. So it ends up back in the same direction if you've got a rectangular or a square block. Okay, so you could be expected to draw, not with the exact angles, but to draw a rough approximation of that diagram, so making sure that your refracted angle is smaller if you're going into glass or plastic or anything like that. Okay, now you might also see a diagram of refraction which doesn't show the rays. The rays just show the direction the wave's travelling in, so the direction of energy transfer really, and that's what you would see if you were looking at light beams coming from a light box. You can also look at it in terms of the wave fronts. So this is what's showing now is the wave fronts in refraction. The arrows show you the direction the ray was travelling in, and those wave fronts really, you've got to imagine you're looking down on the surface of, say, a pond, right? And the white lines are the peaks. So the wave is travelling along, and then it gets to the, in this case, it goes from the air into glass, or if it was a pond, it would go from deep to shallow water, and you can see the change of direction here again, just like before. But this diagram also shows us that in addition to the slowing down, the change of direction, we also get something else going on, which is the shortening of the wavelength. You can see the wavelength, the peak-to-peak distance, is labelled there in the air part, and it's labelled in the glass, and you can clearly see that in the glass the wavelength is shortened because of this change of direction. So wavelength decreases in the slower medium. It's important to note as well that frequency doesn't change. So the frequency for that wave stays exactly the same the whole way through. The speed and the wavelength both change. They both decrease in the glass. Okay. So one other special point to note is the ray that we saw initially was not travelling along the normal. But if you do have a wave travelling along the normal, You still get the slowing down, you still get the decrease in wavelength, but it can't really change direction because it can't get any closer to the normal. So that ray keeps going along the normal line, and it'll come out the other side and stay along the normal the whole way. The slowing down and the shortening of the wavelength both still happen. Okay, but you can't change the direction if you're travelling along the normal. Okay, so that's refraction. We're going to look at diffraction now. Okay, now diffraction is the spreading of a wave that passes through a gap or around an edge. So what you can see on the screen now is what would happen without diffraction, and indeed the thing that matters for diffraction is how big the gap is compared to the wavelength of the wave. And you can see here the gap size is quite large and the wavelength of the wave is quite short. And if you have a situation like that where the gap is much bigger than the wavelength, you get very little diffraction. So the wave basically goes straight through the gap and doesn't spread out. If we go on to a situation now where the gap is a bit smaller, then you get a small amount of spreading on the other side. Okay, that little yellow dotted line is just to show you the angle of the spread. Okay, so if the gap is slightly bigger than the wavelength, you get some diffraction, but not a full amount. And if we get the gap size down to about the same as the wavelength, then the spread on the other side is sort of complete. It goes all the way around and we get a huge amount of diffraction. The maximum amount we can get happens when the gap size is the same as the wavelength, or similar to it. If we go even further, what we'll see is that the wave can't really get through that gap. Diffraction isn't possible. Okay, so the gap is smaller than the wavelength. The wave can't diffract through the gap. And an example of that happening would be the fine mesh on a microwave dish. So a satellite dish stuck to the side of a house. Often these days, to keep them light, they're made of a fine mesh. They use microwave wavelengths of a few centimetres, and so the gap size in that mesh is so small that the microwaves won't diffract through the holes. Instead, they'll actually just reflect off the metal. It's the same thing in the door of a microwave oven. Okay, the mesh size is quite a small gap, a few millimetres, so the microwaves can't diffract through it. But what it does let through is the visible light, which is a much shorter wavelength compared to that gap size. So the visible light will go through those holes. You can see into the microwave through those holes, but you cannot, the microwaves cannot escape. Okay, we'll look at a separate video for reflection and also how reflection means you can form an image.